after that.
Class, we basically have about 1 month left in this, because of through April. That's about it. And then I forgot what the last day of class is.
26th.
You said
26th.
27th of this month. All right. So I'm going to tell you now. Start thinking about the date for your next test. Doesn't matter to me. Remember that. I mean that too, because you have other tests. So figure out when you've got some time to take another test, and then next class period, I'd like to vote on it. All right. I want to get that out of the way. The other thing is, we're getting down to the point where we're going to start actually building, you might say, a block diagram circuits to implement Z-transforms. And I'm going to go through sort of I'll try to do a review too and link all the different transforms that we've gone through. We're going to do some applications of Z-transforms. Today I've got a few things I want to take care of about the Z-transform I didn't get to yet, and also for the inverse Z-transform. Well, we'll see how that goes, but here's one thing I didn't talk about. You know how before, when you had Laplace transforms, you knew that if you had integral from 0 to t of x of t prime dt prime, that one is what? That was the 1 over s x of s. Do you all remember that, class? How many do? Remember, if it's a derivative, s comes in front. If it's an integration, s, it's 1 over s. Do you all remember that? Give me a show of hands. How many do? This is important that you draw these parallels. Now, the equivalent of Z-transforms would be a summation. If you had a summation of x of, say, x of k, where k went from 0 to n, and call this a new function. I'll just call it f of n right here. Now I'm saying this is equivalent to an integration. A summation of discrete time is an equivalent to an integration of continuous time. Does that make sense to everybody? Now, if you take a look at this, and we want the Z-transform, this would be actually equal to what? F of n minus 1 plus x of n. Just think about that. If f of n is really defined as a summation of all the prior values of x of n up to n, right? So you're summing like x0, x1, x2, dot, 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 x of n. Therefore, if you sum all those values to n minus 1, you've got every single value except the last one, and you add it. Do you follow me on this? Give me a show of hands if you do. These proofs are basically just manipulations of things to get them in a form that you can actually do the Z-transform of. Now, when I look at this, I can do the Z-transform of this. I can say that f, if I take a Z-transform, f of z here would be equal to what? That's z to the minus 1 f of z, right? And because there is no value, because the series starts at 0 right here, right? There is no x of minus 1. They call that an initial condition. So it's z to the minus 1. Actually, let me put this one. This is equal to this right here would become, I'll put it to you, yeah, it's z to the minus 1 times f of z here plus x of z. Now, the only thing I've done is take the Z-transform of what's above. Please, you all see that, class? Just be attentive here. I'm not going to try to go too fast. I want to make sure everybody sees. You see the logic. Now, the next thing to do, I want f of z, assuming I have x of z. So I can say that f of z here times the quantity 1 minus z to the minus 1 is equal to x of z. You all agree with that? That's simply just reorganizing the equation. And then if I want f of z here, I can say that's equal to 1 over 1 minus z to the minus 1 x of z. And the way that's usually written, you multiply top and bottom by z, you get z over z minus 1 times x of z. Which means if you knew what x of z was, if you knew that transform, then you would know what the summation of all the values of x and the transform of that. Is everybody okay with that, class? Now that's just that's one of those things that's kind of important to know, because you're going to see there's going to be circuits that we have that we're going to talk about that are going to be summers, really summers of all past values. Then there's going to be summers of just 2 or 3 values, and there'll also be delay operators. This is one important property you have to understand. Now, let's see here. All right, now I got 2 others to talk about. That I don't really want to spend a lot of time on proofs here, but another thing that happens with Z transforms that you have to be aware of is this. Since x of z technically is equal to the summation from n equals 0 to infinity of x of n, z to the minus n. That's the technical definition, right? You have to know that one. If you break that out term by term, that's x of 0 plus x of 1 over z plus x of 2, right, over z squared plus dot 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 plus x of really n over z to the n, and this is really one of those things that's going to go to infinity. I'm just drawing out a bunch of terms. Do you follow me, class? That's the definition of the Z transform. So one of the things, if you look here, I have a function, it's a function of z. Here, I've got each of the individual terms. So if you wanted x of 0, if I took the limit here as x of z as z goes to infinity, do you all see how that's going to be x of 0? Just take a look at that. As z goes to infinity, doesn't all the other terms go to 0 except the very first one? How many see this? All right, so I'm trying to show you this so it sticks in your mind. You're not memorizing just formulas. That should make perfect sense. If you take all the values of z here and let them go to infinity, you only have x of 0 left, don't you? All right, so that's something to see. Now, this next one I'm not going to prove, but if you take the limit of z minus 1 times x of z, and let it be as z goes to 1 here, and this is one I don't use. I actually don't use that one either, but I need to mention it. Then what you're going to get is simply, that's going to be x of n as n goes to infinity. That's the final value theorem, and that's in that should be in your book. If you look in your properties, they'll show these, I believe. Do they have both of these in your books? I think they do, right? Does anybody have the properties page available to you? Do right there. Aren't they in there? They're like the last 2 or 3 properties?
Yes.
All right. So that basically, these I don't really use. I'll level with you. I mean, it's information. Maybe somebody does. Maybe John Hung, we can get him for control systems. He'll tell you it's important. But I don't use it in radar, and I don't use it in transient nonlinear electromagnetics. At least I haven't had a reason to. And I haven't done this with electromagnetic compatibility and interference or any other things that I've used. However, that property may be useful in some other course, so that's the reason I mentioned it, just for completeness. All right, now, after that, I want to tell you that with Z transforms, a lot of times, there's a lot of ways to do this, and I'm not going to go too far down the road. I'm going to just erase this and talk about how you can sort of take the response of any system, just like you did with differential equations. Do you all remember that you could get the solution to the differential equation? It's called the natural response. And then you get the system response or the continuous time response to a diffie Q. Do you all remember this, class? Some say it's the complementary solution, right? And the solution based on the initial values. However you can break it up. You can think of any kind of differential equation solution as part of that has to do with the steady state, whatever the steady state input is that's exciting the differential equation, plus the response of the system to the initial conditions. For instance, on a capacitor and a resistor, if that capacitor had an initial voltage and there was an input-output and just say a switch closed, then you know how to get the transient response, right? But if there's an initial voltage on the capacitor as well as a steady state voltage, all right, at a given frequency, then you would get the response to the continuous, or to the initial values on the capacitor, which is just a decaying exponential if you're looking at the output on the resistor, plus the response to the steady state excitation. I'm just saying that. I'm not going to draw this up there. Do you all follow me in this class? That's based on a differential equation solution. Well, with Z transforms or difference equations, no matter how they fit, you can talk about something where you're going to get two responses that will add together that will make up the total system response. We can say that y of n is really going to be y of n, where it's called a zero input response, plus y of n for the zero state response. Now, I'm not going to spend a lot of time on it, but let me explain this as best I can. When the zero input response, just put this is no initial conditions. Here, this is the response to no x, I'll just say no x of n. There's no input here. So this would be the response to just the state energy for like the -1, and I'll explain this. The value of y minus 1, y minus 2 are like the initial values of the voltage on a capacitor. Think of it that way. Does that make sense to people? I'm trying to say when you get the values of x minus 1, or really y minus 1, y minus 2, that's the initial energy in the system. Even though our Z transform starts for values for n greater or equal to 0, the way that you get initial input, initial energy, call it that, into the system as for like y equals -1, y equals -2. I'm going to show you this in a second, all right? I just understand this. You can break the response of the output, total output, to the response to the initial conditions or initial energy plus the response to the actual forcing function x of n. Now I'm going to draw this out and try to make sure you see this. I thought about the best way to do this. I think this would be good. I don't want to spend a lot of time discussing that particular portion. So let's just jump right in with a real functional form so we can talk about it. Suppose I have a difference equation y of n, this is in your book by the way, minus 1.1 y of n minus 1 plus 0.3 y of n minus 2 is equal to x of n plus 2 times x of n minus 1. So that's a difference equation that determines the input-output relationships of a discrete system. I want to say one other thing. Here we have only x, right? But by the same token, you'll find out your system could have some x1 right here, x1 with a delay. It could have another x2 going as an input, another x3, all giving a y as the output. Do you follow me? You don't have to limit yourself to only one input, one output. There can be multiple inputs, multiple outputs. You'll see that more later in some of your latter courses, especially if you get into digital, really, with Dr. Hungs and his control systems. He may do it, but definitely Dr. Reeves and his digital image processing and digital signal processing. We'll talk about things like that. In radar, we have to do this. We have many, many inputs, many outputs. Just telling you, it's never just one for one. Well, rarely. Let me put it together, rarely. So now for this difference equation, we're going to go ahead and we're going to make it a little more complicated. Now I'm going to say my x of n for this one is going to be 0.25 to the nth power u of n. So it's really 1/4 dying, 1/4 to the nth power. And I'm also going to give some initial conditions. I'm going to say y of minus 1 is going to be equal to 3, and y of minus 2 is equal to 4. Those would be the initial conditions that I just wrote down, the initial values. Think of it in its initial energy. Now, we're going to do this, but I want to do this in an orderly fashion. So I'm going to go through and write the Z transform for each one of these terms. And then we're going to separate them into the actual state response and I'll call it the response due to the forcing function and the response due to the initial conditions. You'll see what I'm up to, all right? So first I take y of n. Well, y of n goes to just y of z. That we know. We're going to take a Z transform of everything. Now the next term here will go as minus 1.1 y, well, better yet, let me not even do that. Let me just do this. I'm going to forget the 1.1. I'm just going to say that y of n minus 1 goes to y of z over z, right? And it's going to be what? Plus y of minus 1. Isn't that right, class? Take a look at the z transform, the definition. Are you with me?
Yeah.
Now that's where the initial conditions come into play. Next, I have y of n minus 2. Well, that goes to what? y of z over z squared plus y of minus 1 over z plus y of minus 2. I'm going to put the values in a second, but follow me what I'm doing. Do you all agree with that? Class, I want to make sure you see this, right? Keep going down the line. X of n goes to just x of z, and x of n minus 1 goes to simply x of z, right, over z, plus x of minus 1. Correct, class? So I wrote those down for a reason. And now I'm going to do one other thing right here. I'm going to go ahead and say that if this is x of n, I know that this goes to simply an x of z. I'll make it equal to it. X of z here will be equal to z over z minus 0.25. Do you agree with me? Right. All right. Now we take that information there and we're going to plug it into this equation once the z transform's done. Let me do it over here. And then we'll separate and you'll see this. All right. The first one's just y of z, right? Now I have minus 1.1, and I'll tell you what, if you don't mind me doing so, I'm just going to erase this y of minus 1 and put in the value 3. And then y of minus 2 and put in the value 4, okay? I'll do it right here. So this is really going to be 3, right? 3 here. And this is going to be 3, right? And this will be 4. Remember, the only thing I've done is replaced the y of minus 1 and minus 2 by the actual stated values. Follow me, class? Those are given in the problem. Are you with me? How many see what I'm doing here? All right. I'm trying to be as clear about this as I can. I don't want to rush through this and just talk about abstract stuff. I want to make sure you see this. All right, now when we do this, we have minus 1.1, and put a bracket. Now y of minus 1 is this transform. Y of z over z plus 3. And then we have plus 0.3. And then it's going to be y of n minus 2 goes to this, which is y of z over z squared plus 3 over z plus 4. And equals, and then I have these two terms. And there is no x of minus 1 here is 0, so I just really need to say it's equal to x of z, right, plus x of z over z, but there's a 2 there, isn't there, class?
Yeah.
Coefficient, or I think, yeah, 2. So it's really x of z plus 2x of z over z. Now, I wanted to do it to make sure you see all the steps.
So, Dr. Vacancy, if you take the zero transfer in here, right? So you expect to your response, which is energy, has a be a function of the steady state and initial condition?
It's always going to be a function of the values that for like n equals minus 1, minus 2, minus 3. Those are called the initial conditions or initial values.
And then we have the steady state, right?
Right, and then it's going to be the response of the system to that alone,
Yes.
plus the response to the forced input, which is this.
So my question is that if we didn't have the initial condition, would that change anything?
Yeah, it changes everything. Then the problem becomes trivial.
Okay,
Because
is it-
then this, if that goes away, all those terms go away, that term goes away, and now you just basically have functions of z only or constant without the initial conditions added into it to cause complexity.
Okay,
In other
so-
words, you can use h of z by itself.
Okay, so that
Give me one
response, which is, again is energy. Can we call it energy without initial condition?
What response? Y of n?
Yes, when we get it.
Yeah, we can call it, it's a signal response. I call it the initial state of the system, I call it an energy.
Energy. But if we take the differential equation response.
It's a difference equation, not differential.
Okay, difference equation. Okay. In that case, for getting response or our energy as a function of the steady state and for initial condition, we need to have those criteria at the beginning, right?
Have to what in the beginning?
We need to have the energy be a function of basically a steady state. Initial condition, our difference equation should have basic initial condition and a steady state boundary, something like that.
Well, wait. The initial they're never stated in a difference equation by themselves. The initial conditions are always broken outside of that.
Yes.
All right. I'm tell you what. Can you talk to the class about
Yes,
this?
yes.
All right. Yes. Go ahead.
What about the x minus 1?
There's no value of x minus 1. Oh well, I tell you the truth. You know what? We could solve for x minus 1, right? But here's the thing. You see this one, the u of n prevents that value from being anything but 0. All right, x, put a minus 1 here, it's going to be 0. All right, and by the way, I'm going to say one other thing. There could be an x of minus 1 that's not 0. Follow me? It's not like it's always that way. There could be a value like that. So anyway, most of the time it's always in y, because y is the out. It has to do with the system's response, so that's where you bottle up all the initial stuff. I'm trying to be as clear as I can. Now, the next thing I'm going to do is listen to me carefully. I'm going to break out y of z by itself with all its coefficients. So now when I do that, what do I get here? I get y of z, and then I get, just follow me, I get 1, right? Minus 1.1 over z, right? And then I get plus 0.3 over z squared. Now what I've done is taken this one, then factored out the y of z here, brought this constant, 1.1 over z here, and then I took y of z out of that one and got 0.3 over z squared there. Follow me? What's remaining? Now I have minus what?
1.1 times 3, so minus 3.3.
Minus 3.3, and I have what is that? 0.9 over, or well, 0.3 and 4 is going to be 0.12, right? Now that's just a constant term there. And then I have what? Plus 0.9 over z, correct? Over z. That's this times this. Do you agree with me, everyone?
0.3 should be 1.2 instead of 0.12.
Ah, you're right. 1.2, sorry.
Nice catch, Mitchell.
1.2, and then I have simply x of z here, and I can put it as what? Just 1 plus 2 over z, if I want. If I want to factor out x of z. Does everybody see this? Y'all with me here? Now, when I look at this, all right, this is the state response, or this has to do with the state response. No initial condition. And this has to do with the initial condition.
That part you just circled 0.9 over z, or not 0.9 over z squared?
It's going to be this times this is 0.9 over z, right? Big summary, right? Yeah, the z squared is here. That's out in front. So now we have that, and this is one thing that he's trying to say, that you can break out the response this way. Now, I can put in for x of z here what I have over there, z over z minus 0.25, and when I do that, I'm going to run out of board space here, but if you listen to me, you'll understand. If I just take this x of z and see it's z over z minus 0.25, so I can go here and put z over z minus 0.25 here, and then it's going to be times 1 plus 2 over z. Now what I've done is now I've got the z transform of that, right? And I broke it out into what would happen if there was no initial conditions. That would be just this equal to this, and this is due to the initial conditions. That's the only thing he's doing, is separating them out. The solution basically is not any, it doesn't get any simpler, but what he's really going to do, and you'll see this, is that you can break out the initial conditions separately. Now, the question I'd have if I was sitting where you were, what does it buy me? At this point, nothing, but what it's going to buy you in a bit is this. Forget about this for now. You all see how I can get y of z by x of z easily, right? And I can get h of z. We're going to find out in time how we can use that information to take just the x of z transform for that function, x of n I put in there, right? I can multiply it by h of z, and I can get an output. Then I can add to that, when I have these initial conditions here, I just multiply those initial conditions times h of z, and I'll get the output due to the initial conditions. That's where we're going with this. It's hard for me to show it right here because I don't have enough board room. But that's the one thing I'm trying to make sure you understand we're going to be doing. And by the way, we might as well just see if we can finish this sucker. So if I'm going to solve that, let's see here. I've got to take, what is this going to be? It's going to be what? Well, that's going to be minus 2.1, isn't it, class? Right there? I just forget it, right? Now I have that, and I can take those numbers to the other side. Let me go ahead and do this. Give me a hand with this too. We have y of z by itself, right? And it's times 1 minus, is it 1.1 over z plus 0.3 over z squared is equal to, and I'll start with the z over, what is it? Z over z minus 0.25, right? Times 1 plus 2, 1 plus 2 over z here, and then I got to take that minus, or yeah, plus 2.1, thank you, plus 2.1 minus 0.9 over z here, right? And then the next thing I do is I'm going to multiply both sides by z squared, because I want the z squared. I don't want anything over z. So when I multiply it by z squared, I'm going to have y of z here times z squared minus 1.1 z plus 0.3 equal to, let's see here, I'll make it z cubed for now, over z minus 0.25 times 1 plus 2 over z, and it's plus 2.1 z squared minus 0.9 z. So then I've got those terms, right? And then I divide by this, and I guess I can just go ahead and say if I divide by that, I have z cubed over z minus 0.225 times the quantity 1 plus 2 over z divided by z squared minus 1.1z plus 0.3 plus 2.1z squared over z squared minus 1.1z plus 0.3 minus 0.9z over z squared minus 1.1z plus 0.3. And basically, I've got that whole thing written out, and that would be my y of z. And this is going to be a rather long one. Now, I've got to tell you one thing. For this particular one, I believe this has complex roots on this thing right here. And this is going to be something where just the y of z itself will be shown like this. The next thing I'm going to tell you, instead of getting a transform the way we're used to, we could do it that way, but the problem is the factoring on this is going to have complex roots. And what I've always told you to do when you have complex roots is complete the square. Do you remember that? And well, if we complete the square on this, we want 2 times something to be 1.1, right? So that's 0.55, and it's going to give us some odd numbers. I'm doing this because it's in the book. I don't know what page it's on, but he does this one. Do you have it in front of you? Well, I can take a look. This is actually on page 379 here. He does factor it out. I'm going to stop right there because this is what I really want to get into. I want to take you through that with the initial conditions business. Then let me go through the next step. This is really what I wanted to do is synthesis. This right here. I wanted to do this to show you that you can actually separate out the response into the response due to the initial conditions and the response due to the actual force function. And frankly, yeah, that's basically going to be something where what I should have done is taken this to the other side, but that's all right, now next is going to be about fabrication. I do this with that differential equation because we have not really worked any problems with initial conditions. That's the reason I took the difference equation and broke it down that way. This is a little more complicated one. Now next, this gets into the actual fabrication. If I have something like this, if I have y of z, say it's equal to 1 minus 0.6 over z plus 0.8 over z squared, and that's equal to 4 times x of z. I'll tell you this right now. With these difference equations, really we know if we multiply both sides by z squared, we'd have z squared minus 0.6z plus 0.8 equal 4z squared. Do you follow me? You could easily get the transfer function h of z. Do you follow me on that, class? Now I didn't want to start the transfer function, I want to start here because at this point, if you get something where you have y of z, the highest power is 1, and z to the minus 1, z to the minus 2, highest power here is just going to be 1. We can build a circuit with delay operators that will go ahead and achieve this input-output relationship. Let me explain one thing. Anytime you see the D here, that is delay. by 1. If you, for instance, had a delay operator here, and the input to that was y of n, the output would be y of n minus 1. It would delay the output by 1. Follow? That's the only thing a delay means. You'll see a capital D. Did you ever do anything with delay lines or anything like that with your JK flip-flops? You had things, didn't you have something like that where you, no? You had JK flip-flops,
Yeah,
right?
yeah.
And you had counters and, you had adders, subtractors, right?
Digital logic circuits covered all that.
What's that?
I said digital logic circuits covered
Did they
all.
cover delay lines in there?
Not exactly. Nope.
There might be another term for it, but anytime you have any kind of circuit with a clock, you can have things stream in serially, right? Asynchronous serial ports, right? Both of those. The synchronous port is easily get a delay on. You can easily delay anything by 1 clock cycle. I don't know what they term it these days. But anyway, I want to show you this. Now, if that is the case, if you think about this, if this is y of z here, a delay operator is really z to the minus 1, and the output would be just z to the minus 1 times y of z. Does everybody follow suit on that one? That's assuming no initial conditions. Y'all with me on this? Just take the z transform of that. It brings out a z to the minus 1. So if I look at this right here, and I want to realize this circuit, I know I can do it several ways, but I'm going to do it, I think the first way, I'm going to do it with the delay operation. So here, I'm going to have my input x of n going in, and we're going to realize this with the delay operator. The first thing I notice, there's a 4 here. So now I multiply by 4. And it'll just be a box like this that says 4, and then it comes out. Now next, do you remember when we did this with the Laplace transform, how we built things first with block diagrams and then with op amps, how we had those what? We had the 1 over s operation. Do you remember that? All right. Well, next, and the 1 over s was really an integrator, right? Next thing we're going to go ahead is put a summer here. And now what we're going to do is say, I take a look at this, and you look, here's my y of z here, or y of n, call it y of z, or y of n. I'm going to take this and put the delay operator. That's going to reduce it by 1. Just follow me on this. Then I'm going to go ahead and multiply by 0.6 minus 0.6 here. I'm going to take that and sum it. Another delay operator brings that as come down and put 0.8. And now take that up to here as a summer. And now we've realized that function without writing the formal difference equation. This will do it because the delay operator brings it out of z to the minus 1. If you take a look at this, you could do it in the z domain if you wanted. If in the z domain, this would just be what? This wouldn't be a delay operator, it would be z to the minus 1, right? And this would be z to the minus 1. Follow me on this? How many see this right here? So you can assume these things, delay operators are just z to the minus 1 in the z domain. And if you look at this, if you're in the z domain, then this becomes x of z, right? Times 4, 4x of z, right? That's going to the output right there. And add to that, it's going to have the output is going to be the minus 0.6 and the minus 0.8 by 2 delay operators, and that should do it. And that is in your textbook. You have the, I'll tell you the page this is showing on. He shows you this on 381, I believe. Oops. Take it back. This should actually be a plus and this a minus, because this should be on the other side. Let me just take it, do this for you. This is y of z, right? Follow me. When I take it to the other side, it's equal to y of z divided by z times 0.6, right? And then it's going to be minus 0.8 times y of z over z squared. I'm sorry, heck. This plus this. Follow me on this. This is the way it should have been written. I should have done it this way. Does everybody see this here, class? I want y of z on one side by itself. It's equal to 4x of z. Well, there's the 4 x of z coming through here, right? Y'all follow me? Then you have to add to that, well, y of z over z, that delay operator is z to the minus 1 times 0.6, add to that, and it has to be minus 0.8 times y of z, again with 2 delays down here, z to the minus z squared, 1 over z squared times 0.8, and it goes back there, but that's a minus 0.8 there, this y of z. How many see this right here? You follow me? This is basically the same thing we've done with Laplace when we use Laplace transform to do block diagrams. It's the exact same thing, only for this one it's discrete, and we have delay operators instead of integrators or differentiators. That's the thing. They're all delay operators on this one. And that's how that goes. Now, I want to tell you something about this. There's a lot of different ways to synthesize these circuits, or to actually show block diagram drawings. This is only one of many. One other thing I can tell you about for this one, y'all realize we could get a simple transfer function, h of z, right? And we could go ahead and we could break it into partial fractions, and we could get 2 separate circuits that we realize each one of those partial fractions, and then add summers to it. So there's many ways. This is one way, and it's commonly used. What I just showed you is basically get y of z as a function of everything else, and then construct it with block diagrams this way, where you have this is one way. All right, next after that, going in here. I'm going to mention this about the frequency response. He talks about, now frequency response is something that we've talked about already when we did the DTFT, and it's really, honestly, it's just the same thing here, but I need to talk about it explicitly. So, if you have a function that's h of z, I'm just going to put one up there, and we're looking at the frequency response. Is anybody going out to the game, by the way, next Saturday? You are? That's it? I don't know what the student rates are. I'm asking this because I've got, in the back of my mind, I have got a lot of questions about this I have to deal with. Did they put student rates out there? How much are they? 40? $40 to get you there?
Just to go in.
Oh, tickets. Never mind. Did they have any kind of a group rate to get up there?
They have student packages. They're expensive.
Can anybody give me look, I'm chair of the Senate. I kind of need this information. Does anybody have an idea how much they cost? To go up there in a hotel room. Is it less than 3,000?
The official ones start at around 2,000, I think.
It's 2,000?
I think that's where they're starting at on the official site. For, the official
And that's
ones.
through Monday? Or is it just the...
Yeah, I think it's through Tuesday.
All right. Here's the reason. A lot of parents are mad it costs so much. And of course, I just need to make mention of this so that maybe something can be done. I don't think anything can be done, but I hope so. Because this is the first time ever, right? Yeah. I would want to go if I was. Yeah. I'm not saying you're going to go, but I would want to go. It's too darn bad. It's up that far away. It's not in Atlanta or something. Yeah, well, all right. Sorry, I got a lot on my mind right now. If you have any h of z, and I'm going to just come up with one. Suppose I have z squared minus 2z over z cubed plus 3z plus 2. Just assume that's it. One of the things you're going to be asked to generate is the frequency response. You listening to me now? You're going to ask to get this down, and you're going to need to at least have an understanding to see if it's high pass, low pass, band stop. The way to do it is let z be equal to e to the j omega. What that means is normally z is what? Z is normally some radial distance rho e to the j omega. Here we just make rho equal to 1. Now, basically what you have is this. You have h of omega here, which is really the dt ft of the system. You follow me? Again, it's assuming x of n is 0 for values of n less than 0. So if you do that, then you're going to get e, well, when you get a squared operator, it's just e to the j times 2 omega. This is minus 2 times e to the j omega over e to the j 3 omega minus 3e to the j omega plus 2. I'm doing this explicitly so you all see this. When you want the frequency response of this, you start at omega equals 0. When you look at omega equals 0 here, what is e to the 0, class? 1. So when I look at h of omega equals 0, that's really equal to 1 minus 2 over 1 minus 3 plus 2. Y'all,
Plus 3.
pardon me?
Equation.
Oh, I'm sorry.
Yeah.
Wait. What did you say?
The first one is plus 3z, so should it transfer to plus 3e?
Ah, plus. Yes. Thank you. All right. What's that value going to be? You're right. That's 1 over 6, right? Right?
Negative 1 is
Pardon me, minus 1/6. Actually, you actually want magnitude of this. So just do it that way. It's going to be plus 1/6. Now, the next thing, just let me finish this. That's where it starts. Next thing you do is go to e to the j, usually pi over 4, and I'll tell you why. Because this is going to be e to the j pi over 2, which is really what? J, isn't it, class? This is going to be, you can do pi over 4 here. E to the j pi over 4, let me break it down for you. E to the j pi over 4 is really equal to 1 plus j over the square root of 2. It's because this is cosine of pi over 4 plus j sine of pi over 4. The cosine and sine of pi over 4 will 45 degrees or 1 over square root of 2. So it goes to 1 plus j. If you have e to the j pi over 2, that's simply j. E to the j pi is minus 1, and you can fill in all the other things. But for the frequency response, you usually start at omega equals 0. Then you take omega equal to really pi over 4, then pi over 2, then really you're going to go the next thing, 3/2 pi, and then, 3/4 pi, and then pi, and what you'll have then is information from 0 to pi, and the magnitude will always be the same on the other side for omega going negative, all right? So you can take the magnitude will always be the same on either side of that. What I mean to say is this, you only have to go from 0 to pi. You don't have to go from 0 to minus pi because the magnitudes are the same, so you can just take and reflect the function. All right, class. I'll talk to you next time. And I'll have more to say about these Z transforms and the synthesis next time.
It's not hard to like